Hooks and coprocessors are a match made in heaven. Let's look at the new Brevis hook that implements a loyalty program on AMMs and basically just illustrate. I think it's a perfect example of how coprocessors can be used in hooks. Hello, I'm Peter, and I talk about crypto from a product perspective. You can find me on Twitter at P_E, and also check out my newsletter if you're interested in that stuff. Okay, so let's look at the Brevis blog post. They recently put out this blog post with a kind of proof of concept hook that they developed, which I think illustrates what coprocessors can do really well in a very simple way. So if you're not familiar with Uniswap v4 hooks, I won't go into much more detail on them, but basically they allow you to kind of create callbacks on different kind of actions you take in your Uniswap v3 style AMM. So specifically in this implementation, we're using the fee override that basically allows us to kind of specify dynamic fee. So that's going to be used as a way to kind of differentiate between these different tiers in a loyalty program. So let's start by just checking out their video.
Introducing the VIP discount hook on Uniswap v4, a hook supported by Brevis to trustlessly read and compute a user's WBTC USDC trades for the past 30 days and determine whether the user is eligible for a trading fee discount based on their total trade volume. To try out this testnet demo, first you need to connect wallet and claim some testnet WBTC and USDC from the faucet. Enter the amount of USDC you want to trade and approve USDC. If you haven't traded between these two tokens in the past 30 days, you will see a note saying, "You may enjoy a fee reduction by activating a VIP status via Brevis." Complete a trade to activate your VIP status. Once the trade is confirmed on-chain, you can activate the Silver VIP status to get a 20% discount on trading fees. To activate the Silver VIP status, the VIP discount hook queries a zero-knowledge proof from Brevis. Brevis will compute your WBTC USDC trades for the past 30 days and generate a succinct zero-knowledge proof of your total trade volume.
The interesting thing here, I think,
proof is generated,
is that kind of the user is requesting the proof to be created.
Contract to verify. You can also view the result of your ZK proof verification on-chain. As you can see, we have successfully verified our Uniswap sum volume proof in the hook contract. Once verified, you can trade with a 20% Silver VIP discount. The specific VIP tier and discount are based on a user's total trading volume over the past 30 days. A user gets a 50% discount as a Gold VIP when they have traded more than $1,000. The demo here only shows how Brevis proves a few user transactions, but Brevis is way more performant than that. With the same gas cost as in the demo, Brevis can generate a ZK proof of computation for thousands of transactions in under a minute. It can be more than 1,000,000 times cheaper compared to on-chain smart contract computation. Hook contracts can now implement cost-efficient data-driven features for how Uniswap pools, swaps, fees, and LP positions interact, all based on dynamic and trustless data computation.
Yeah, so this is definitely a good point here that it's not just applicable for fees; it's kind of applicable for all aspects of hooks. Really, could kind of utilize this. I think the rest of the post, they basically talk about how why this use case is relevant. Yeah, in centralized exchanges, we do have these kind of VIP trader programs that encourage you to basically really stick to one exchange because you're just going to get these kind of tiers of rewards there. And how in DEXs it just has been really expensive, right? There's sort of the ways to do it currently for DEX would have been either you're kind of actively on-chain tracking. During every single swap, you're now starting to remember, okay, this user did a swap and like that's the amount. Let's sort of add and store some sort of value there, which is really expensive from a storage perspective. Or alternatively, you could use like an off-chain indexer, and then kind of build an oracle that would query that off-chain indexer and push data, which of course would not be as trustless as using a coprocessor. So yeah, I think this is a really, really nice use case, and great that they're kind of highlighting that the computation design patterns here are synchronous. And the asynchrony, like how does that play out here? I think we saw it in the video when the user wants to kind of assert that they fit in a given loyalty tier, they then have to trigger the proving to happen, right? You could have systems that sort of automatically refresh these proofs. For example, maybe every month the system just sends kind of a batch proof that basically just kind of captures all the users that are eligible for these different tiers. There's definitely kind of different ways to make this simpler. I don't think the future of this is that users will sort of continuously have to initiate these client-side kind of proving flows, but it's definitely a very simple way to demonstrate it. And then they kind of talk about other examples that could be implemented here. But I just want to just dive in and just show the hook code, because I think it's really simple and clear to understand kind of what's going on here by looking at the code itself. So when you're writing a hook, you typically implement a couple of these kind of before and after hooks, sort of after swap and things like that. But the other thing you can change is you can set a dynamic fee, right? So if you can override this get fee function, you can have kind of any kind of fee calculation you want. So in this case, basically the logic is very clear here, right? So if we are in some of these different fee tiers, we're basically getting this kind of either 50% reduction in the fee or a 20% reduction in of the fee if we're in the silver tier, right? So that's kind of what we want. Now the interesting question is like, where does the fee tier come from? So if we look here, standard tier, it seems like it's pulling it from this kind of Uniswap sum volume function, right? Get attested sum volume. So the idea is there's really getting that attestation, that proof for what the user's historical trade volume is, right? And then here we can see that if the volume exceeds a certain threshold, that's where you get the gold tier. And if you've done kind of any trading, you'll basically get silver tier, and otherwise you won't have a specific loyalty tier. So if we jump in there, this is, I think, the key function, right? So the key function is basically this is the endpoint where we can submit the proof. And that's what allows the coprocessor to really get the data on chain, right? So we have this proof submission, and then it sort of gets verified and stored in this contract, right? And so I don't really understand all the details behind the specific circuits they're using and so on, but the essential idea of how these coprocessors work hopefully is clear from this explanation. And I think the broader thing here is I think hooks and coprocessors obviously work very well together, and like maybe just how powerful this use case is can be illustrated by looking at how are we doing it a year ago, 2 years ago. And I think the ribbon kind of RVol example is a great illustration of that. So ribbon is a protocol that was running these kind of structured product vaults that every week would hold an options auction. And these vaults needed to basically be able to price these options. And in order to price an option, you need to know what the volatility is, right? And so there's kind of two ways of typically looking at that. You can look at implied volatility, which is you actually look at options prices in the market and then you infer the volatility from that, or you can use historical volatility. And Ribbon chose to do the latter approach. They chose to say, okay, can we look at historical volatility of the asset prices and basically estimate that, and then use that to kind of price these options and initiate these options auctions with a decent starting price, like a fair starting price, right? So they created, in order to get the volatility, they had to create this really, I think, expensive and cumbersome and really inefficient and accurate implementation of a volatility oracle through necessity, which was they had a Chainlink oracle, which basically could provide the price. They had this volatility oracle, which we're seeing here, the vol oracle, and then they had this commit function, which basically anybody can call and create a new price observation, right? Commits an oracle update. So what basically this contract would then do is, like, you call commit, it pulls Chainlink, gets a price, and then it updates the historical volatility with this new price, right? And so it just keeps like whatever prices it has observed, it will basically get a trailing kind of volatility window out of those prices. And yeah, this is obviously, and then how like who's actually going to send these commits? Obviously, you can't guarantee that people will, so they had to use keepers as well. So they had to pay keepers to sort of on a regular basis call these commit functions on these oracles, and then you had to basically they had to deploy and maintain this public goods contract effectively for whatever asset pairs that they were interested in. Yeah, and so clear issues here, right? Chainlink kind of by its notion is a little bit delayed already. So now if you're doing these commits, then there's a lot of uncertainty around like when you actually call this commit function could really change the outcome of the answer here. Obviously, volatility that's sampled that is only an approximation. You kind of this choice of the volatility window, and then you're paying the keeper, you're paying the gas. So all this is kind of to show basically that we were highly constrained to do these use cases. And the reason I bring up a volatility oracle because it sort of illustrates like with hooks and coprocessors, you basically get two new ways of doing volatility oracles. So the first way is of course with a coprocessor, you could basically just the Chainlink oracle. There's a clear record on chain of what prices it had at each point in time, right? So all we need to do is some historical query over that data, and we could produce a volatility estimator, a historical volatility estimator. So this is something I think that coprocessors will be very good at. So you'll be able to sort of say, hey, I want to request a volatility value estimated based on kind of last month's Chainlink prices and kind of sample it at this range. And you'll be able to basically publish that proof on chain fairly efficiently. The other way to get an oracle, if you wanted a synchronous version, would be to use a hook, right? So you could use a hook directly on the price changes, right? So if we kind of think about how TWAP oracles worked for Uniswap v3, right? It had a built-in TWAP oracle which would just kind of keep caching the prices. Well, you could layer on a volatility oracle as well, right? So every time we get a new price, now it recalculates not just that price, but it also recalculates the trailing historical, 30-day or 15-day or whatever volatility. So really we're getting these two new ways of implementing different types of computations that require kind of access to historical state. We get the coprocessor way, and actually we can sometimes have just use the hooks if we're just really looking to use something that's maybe dependent on prices or historical trades or something like that. Obviously with the hook, you need to make sure that the pool is going to have sufficient liquidity so the price is actually going to be accurate. I think that's not an easy question, but with a coprocessor, you really don't have that distinction. So I think it probably will be more natural and more common over time that we'll just get this volatility type data posted through a coprocessor along with many other things. Hopefully this illustrates a little bit how coprocessors and hooks can work together very well, and why I think we're just scratching the surface. I think it's a wonderful example from Brevis. If you like this, subscribe to the channel and also check out my newsletter at newsletter.auditlist.com. Thanks.